Hello, I'm Fast Lawyer. Today we're doing a Let's Play and early impressions, really initial impressions, for Edda Physics 1 VR. A game? Is it really a game? Let's call it an educational experience that was released on the Steam store November 25th, 2024. It normally retails for $30. It's on a release sale 30% off. That's still going on. And I received a free Steam key through the Steam Creator Connect program to review this game, and I'm testing it out on the Meta Quest 3 using link cable on my RTX 3080. Sorry. Edda Physics, there's one for schools. That's not the one that we have. We have the one that's the consumer version. And you see there's information here on what's available for schools. So this is a pretty neat app. This is at the forefront of some experimental educational experience that uses VR to help students learn, and we in VR as consumers get to experience some of that. So this is pretty exciting. We're going to learn physics in VR. Let's see. Oh, by the way, these are the only settings available, so just language and the license information. So let's click on Archimedes' principle, the first lesson in physics. Now this
Hello
is
and
voice.
welcome to Archimedes' Principle. Today you will conduct an experiment to hopefully come to the same insight that Archimedes did 2,000 years ago. Archimedes' principle states that an object submerged in a fluid is buoyed up by a force equal to the weight of the fluid displaced by the object. To your left, you have a whiteboard with formulas and information that can help you through the experiment. To your right, you have a whiteboard that will be used to record important values throughout the experiment. We will start by examining how the volume of a body affects the fluid it is submerged in. In front of you, you have two containers. One container contains water while the other container is used to measure the amount of water displaced when an object is submerged in the water. To your left, you have a number of different spheres. The larger spheres have twice the volume of the smaller spheres. Try picking up the small gold sphere and place it in the large container with water. When you place an object in water, you can observe an upward arrow representing the buoyant force and a downward arrow representing the gravitational force. Observe how much water is displaced by looking at the small container and the scale beneath it.
Okay, so a couple things to notice is that we have liquid gold, mercury, salt water, ethanol, and liquid hydrogen. And over here we have the formula, which is F, the buoyant force for the object, P, the density of the displaced liquid, times G, the gravitational force for the displaced liquid, and volume for the displaced liquid. And here we have the volume, weight, density, weight, buoyancy, density, weight for the different spheres. And so let's start our experiment. She said to do the little gold sphere. Now, be careful. I hit back by mistake, and it took me back to the main menu. So be careful. It's very easy to do that. I kind of wish that button was somewhere else, because it is very easy to hit it by accident.
Is now recorded on the board in front of you.
Mm-hmm.
This weight is, in accordance with Archimedes' principle, identical to the buoyant force that the object experiences. Remove the sphere from the large container. You will now test submerging the large gold sphere, which has twice the volume, in the container. Again, observe how much water is displaced into the small container using the scale. The volume of displaced fluid should be approximately twice as large.
Yeah, it is.
With the help of the scale, you can observe the weight of the displaced fluid, which will also have doubled. Furthermore, in accordance with Archimedes' principle, the total buoyant force has also doubled. After testing the impact of volume on buoyant force, we will now examine the impact of density. Try submerging the red plastic sphere in the container. Observe how much water the sphere has displaced and the weight of the displaced water.
Now it says red, but it kind of looks like orange to me. The button is red right here. The button is red. Don't touch it. Be very careful. Like I said, I touched it by accident.
Remove the plastic sphere from the container and repeat the same procedure with the large gold sphere. Observe that the volume and weight of the displaced water are identical in both cases. This means that the buoyant force generated is also the same in both cases. Plastic and gold do not have the same density, i.e., their mass per unit volume differs. For this reason, the gold sphere sinks to the bottom while the plastic sphere remains floating. Density, therefore, has no direct impact on the buoyant force that the object experiences, but it plays a crucial role in the object's buoyancy. We will now test what happens when we vary the density of the fluid in which the objects are submerged. On the container in front of you, you can regulate the density of the fluid using the control next to the container. Submerge the large styrofoam sphere in the left container and note the weight of the displaced fluid. Now try decreasing the density of the fluid to that of ethanol and observe how the weight of the fluid changes.
Okay, styrofoam. I'll put it down. Very interesting. Wow. Well, look at that. Okay, it's finally stabilized. And okay. There we go. Fine one. Wow. Okay. And submerge the large styrofoam in the left container and note the weight of the displaced fluid. Yes. Now try decreasing the density of the fluid to that of ethanol.
Now you will examine how the buoyant force varies based on the fluid's density. Remove the styrofoam sphere from the container. Change the density to water and observe the buoyant force on the small gold sphere.
Okay.
Now change the density to that of liquid gold and again observe the buoyant force on the small gold sphere.
Okay, liquid gold. I don't think I've ever seen
As you
liquid
can
gold.
see, you can make the small gold sphere float when the fluid's density is higher than the object's density, even though the object has the same volume and weight. You are now finished with the experiment. Great job.
Thank you.
You can return to the menu by clicking the back button.
Okay, we're going to click the back button intentionally this time. But yeah, it is very easy to click it by accident, so be aware of that. So that was an interesting lesson. Let's try Newton's law. Or do you want to try? No, let's try Newton's law, because after Newton's law, we can do the theory of relativity.
Welcome to Newton's laws of motion. This lab will help you understand what went through Isaac Newton's head when that faithful apple dropped. Newton's first law, law of inertia, states that an object at rest remains at rest, and an object in motion continues in a straight line at constant speed unless acted upon by an unbalanced external force. Let's see if this is true. In front of you, you have a frictionless air hockey table with no other forces present. To your left, you have a handful of objects with varying weight and velocity, and to the right, you have a whiteboard, where you can observe measurements regarding the objects you place on the table. Place any object with a velocity of 0 meters per second on the air hockey table.
Okay.
Start the simulation by pressing down the Start/Pause button. Observe how the object remains at rest since the resultant force is 0.
Of course, yes. Unless there was wind or
Pause
something.
the simulation by pressing on the button once again. Place a new object with a velocity of 1 meter per second.
Okay. Oops. I don't know if you heard that. That was my guitar.
Start the simulation and observe how the object remains in the same uniform linear motion at 1 meter per second.
Okay. Yes. I guess so.
Above the air hockey table, there are force vectors which you can grab and stick onto the objects. Grab 2 vectors of 1 Newton and apply one at the front of the object and the other one behind the object. Now, 1 Newton should be applied both in and opposite to the direction of the object's uniform motion. Start the simulation and observe how the object remains in uniform motion at 1 meter per second. Place another object with a velocity of 1 meter per second next to the first and apply instead of force of 2 Newton both in and opposite to the direction of the object's uniform motion.
Okay. Apply instead of force of 2 Newton both in front. Okay.
Start the simulation. How does what you see confirm Newton's first law? Select one of the objects on the table and change the force to 2 Newton in the direction of the object's motion and 1 Newton force opposite to the direction of motion.
Okay, that'll be interesting. This will be an interesting experiment.
Start the simulation and observe how the object's velocity now increases, i.e., the object accelerates. According to Newton's first law, what causes this?
Yeah, and that makes sense.
Pause the simulation. You have now demonstrated Newton's first law.
I have. Okay.
Newton's second law explains how the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. This is expressed with the famous equation
force equals mass
equals ma, where F is force, m is mass, and a is acceleration.
I'm having flashback to high school physics, yes.
Place an object with a mass of 5 kilograms and a velocity of 0 meters per second on the table.
Okay.
Then apply a force of 1 Newton in the direction. Start the simulation and note the magnitude of the acceleration that you can see on the whiteboard to the right. Pause the simulation. Double the mass of the object by selecting the red 10 kilograms object on the table to the left. Again, apply a force of 2 Newton to the object, but this time to the 10 kilograms object. Start the simulation and note the magnitude of the acceleration. Clear the table of all objects by pressing the reset button.
Yeah, it is going faster. Wow, it's accelerating. Okay, interesting.
Consider how the pattern in the table on the whiteboard relates to what Newton's second law states.
Yeah, force equals mass times acceleration, yes.
Do your observations align with the statement of the law?
Yes, it does, actually.
You have now proved Newton's second law.
We did, okay.
Newton's third law states that whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first.
Okay. I think I understand.
To study this, place an object in the middle of the air hockey table and choose any force to apply to one side of the object.
How do I place it in the middle? I think you need a room scale for this. I'm playing seated, but we'll do the best that we can. It doesn't matter which object. Well, you know what? It doesn't matter.
Start the simulation and observe the force F that the edge of the table experiences, indicated by a pink force arrow. Also, note that the force F asterisk experienced by the object is of the same magnitude but in the opposite direction, indicated by a light blue force arrow.
Okay.
Pause the simulation. Clear the table before proceeding to the next step.
Okay.
Place the red object next to the left edge of the table and the blue object next to the right edge of the table.
Okay.
Choose any force to apply sideways to both objects so that the object accelerate the two objects towards each other by starting the simulation and observe the forces F1 and F2 acting on the two objects upon collision.
Yeah, I do.
Does
Very
what you observe
interesting.
align with Newton's third law?
Yes, it does. For
Congrats.
every action, there is a
You
reaction.
have now explored Newton's laws of motion.
Okay. Those are the 3 laws, and that's what we're looking for. Okay. I guess we go home now. Okay, so now we're going to do something a little bit more compelling, the theory of relativity, or should we go right into nuclear physics? We'll do theory of relativity. So we're going to leave the Coriolis effect.
Welcome to Einstein's theory of relativity. In the first part of the lab, we will investigate the concept of simultaneity under Einstein's special theory of relativity.
Yeah, time seems to go...
A theory that explains how inertial observers in relative motion disagree on the timing of events at different places.
Yep.
If one observer thinks that 2 events are simultaneous, another might not.
Yeah, that's true.
You are currently in Earth's reference frame. In front of you to the left, there is a cart. At the center of the cart, there is what looks like a lever or a small traffic sign. When the simulation starts, photons, i.e. light, will be emitted in both directions from this midpoint. On the table, there is a control that determines the speed of the cart measured as a percentage of the speed of light.
Okay.
Start by adjusting the control so that the cart has 0% of the speed of light.
Is it already at 0%, or do you have to bring it further down?
What do you think will happen to the cart when you press start?
Nothing. It will not move at all.
Look closely at the photons that are emitted from the center of the cart. Do the photons hit the rear and front ends of the cart simultaneously?
It looks like it.
We will now investigate what happens when the cart travels at the speed of light, relative to the Earth. Adjust the control so that the cart's speed is approximately 75% of the speed of light.
Okay.
Start the simulation.
Okay.
Observe when the photons hit the front
it
and
definitely
rear
looks
ends
like
of the
it's
cart.
hitting the rear
Does
first.
it happen simultaneously?
No.
If not, what could this be due to?
Time is relative. It doesn't make sense, though. I got to admit, to me it doesn't make sense, but that's the answer.
We will now change reference frames. Press the reference frame button. You are now on the cart, i.e., in the cart's reference frame. Let the cart's speed, relative to the Earth, remain at 75% of the speed of light.
Okay.
Start the simulation.
Okay.
Observe when the photons hit the front and rear ends of the cart. Does it happen simultaneously?
It appears so, yes. So it's relative. It's going slower.
According to the observations you have made in all steps, is it true that 2 events that are simultaneous in one reference frame must be simultaneous in another? Why or why not?
No, they don't have to be simultaneous in another reference frame now.
Return to Earth's reference frame by pressing the reference frame button. In the next part of the lab, we will investigate the phenomenon of time dilation, a phenomenon very closely related to simultaneity. Time dilation describes how the perception of time for an event can differ between 2 reference frames in motion, relative to each other. This means that an observer in relative stillness will experience processes in a reference frame moving near the speed of light as taking longer, compared to the experience of an observer within the moving system. Similarly, the observer in the moving system will experience time as passing more slowly for the observer in the stationary system. This perceived time extension is what we refer to as time dilation. Start by pressing the time dilation button.
All right.
You are currently in Earth's reference frame. In front of you to the left, there is a cart. On the cart, there is a photon emitter, and parallel above it, there is a round plate that absorbs photons. When the simulation starts, a photon will be emitted from the photon emitter to the round plate. On the table in front of you, there is also a clock that will show how long it takes for the photon to travel from its starting point to its end point. Above the platform of the cart, you see a clock that measures the time for the same event, but from the cart's reference frame. Set the cart speed to 0% of the speed of light. Start the simulation.
Okay.
Observe, with the help of the clocks, how long it takes for the photon to be absorbed.
Yeah. About 1 second. Yes.
Now try changing reference frames by pressing the reference frame button.
Okay.
Start the simulation and observe the event again.
Okay.
Does it take the same amount of time for the photon to be absorbed in the cart's reference frame?
Yes.
What do you think this is due to? We will now return to Earth.
Okay.
Press the reference frame button. Now change the cart's speed to 95% of the speed of light.
Okay. As you move closer to the speed of light, that's when time starts bending.
Start the
Or
simulation.
time dilation starts happening. Did she say 95? Or 96? There we go.
Observe how long it takes for the photon to be absorbed. Does it take the same amount of time on Earth as in the cart's reference frame?
No. Just a little bit.
Reflect on how far the photon must travel compared to the previous step when the cart's speed was 0% of the speed of light.
Yeah, that makes sense.
Switch to the cart's reference frame by pressing the Start the simulation.
Okay.
Observe the event again.
Whoa,
Note
a lot
that the
faster.
time it takes for the photon to be absorbed now matches the clock on the cart.
Yeah. So it felt a lot slower, even though the time clock was the same.
Is the distance the photon must travel in the cart different? Why did it take longer in Earth's reference frame for the photon to be absorbed when the cart's speed was 95% of the speed of light, compared to when the speed was 0%? Congratulations! You have completed the lab regarding Einstein's theory of relativity. Hopefully you have gotten a relatively valuable insight into phenomenons that leave many people today pondering.
I think I'm more confused now. Let's go to the... Wait, we never clicked on simultaneity. What's going on there? Okay. There's 3 more lessons, but I'm actually not going to do them. I was interested in doing... Actually, they're all interesting. The Coriolis effect, electricity and fields, and nuclear physics, but we're just going to leave it there. This is one of those things that it doesn't feel right to score it. What I'll say is that I enjoyed the lessons. I would say $30 though, normal price. Keep in mind it's 30% off. Is a steep price, but I think the lessons are very well done, and you get like a visual representation, and it feels like you're physically there versus watching a video on YouTube or something like that. So I like to see more content. That would be my biggest gripe, and go more in depth. I think the problem is that a lot of physics involves very advanced math. So you can teach concepts, but actually doing the math is the hard part. At least that was my experience doing physics. I was in advanced math back in high school. I took advanced calculus and all that. So for me, physics wasn't that difficult, but the concepts you can see the visual representations and kind of get it, but until you do the math, I don't think you really get it, because the math is really the important part that brings it into the real world, and makes it something more than just concepts. I guess what I'm saying is the proof is in the pudding, and the pudding is math. These are all mathematical equations, and you have to really do them, be able to do them to understand them. So to me, that's the trickiest part of physics. Is the actual advanced mathematics involved. But like I said, this is very interesting. If you're interested in learning physics through VR, I think this is very exciting, and I do recommend this. But you have to be into the material in order to pay the premium price, but also to enjoy it and really make the most out of it. But yeah, this is very well done. I thought the lessons were very well done. But they weren't the most in-depth lessons I ever learned, because like I said, there's a lot under the hood that they glossed over. But as far as just concepts, great job. I think they really did a good job of showing these concepts, making you do these like experiments and seeing how they work, and so you at least have like a basic grasp of these very complicated concepts. But again, the math is the thing that holds it all together. Anyways, I'm Fast Lawyer. This has been my Let's Play. So I'm not going to score this experience, because it's an educational experience, and I found it educational. So I think they did a good job of being educational. So for those looking for that target audience, I think this is good. And I wish I had this back when I was going to physics in high school. Would have made learning a lot more fun. But anyways, I'm Fast Lawyer. I do recommend this game, but I'm not going to score it, or this educational experience, but I'm not going to score it. This is Edda Physics 1 VR. If you enjoyed my video, don't forget to like, comment, and subscribe. And as always, have a wonderful day. Goodbye.